Hi there. In this video, we're going to be talking about surface integrals. So we'll start by looking at the xyz plane. We have a differential surface area element in the xy plane. And since it's in the xy plane, the sides are dx and dy. So the surface area of this differential element, which we'll call ds, is just simply equal to dx dy. So we want to create something new. We want to try and understand what is the surface area in a certain direction. And that direction is in the direction perpendicular to the surface. So this surface area element is in the xy plane, and the perpendicular component is in the z direction. So the perpendicular vector is the unit vector k. So we create this new quantity called the vector area. And it's simply just the product of the differential element area ds in the direction of k. So it's dx dy in the perpendicular direction. So we now want to extend this to an object in 3 space. So if we have any kind of object, and we now take a differential element that's ds, then the perpendicular vector is actually the unit normal vector. That's n. So we can think about this vector area ds. So we would write ds as we would normally do, and then show a bar on the top to show that it's a vector area. And this is just equal to the differential surface area element multiplied by the unit normal vector. And in the previous videos, we saw that the unit normal vector is calculated as the ratio of the gradient vector divided by the magnitude of the gradient vector. So we can now compute what a surface integral actually is. So what a surface integral is just taking the integral or integrating a certain function. It can be a vector function, or it can even be a scalar function. So we'll start off with a scalar function, some scalar function d, and then multiplied by the vector area. So this would be a surface integral, where d is some function of x, y, and z. So this is a scalar function. So how would we interpret this? What would be the interpretation of a surface integral? Well, we could think of d as maybe being the temperature distribution. So the temperature at a certain point on the object depends on at which point you are on the object. And if we're integrating this along the surface, and if we're integrating it at each point perpendicular to the surface, then what this surface integral actually tells us is basically the heat radiating. It gives us information about the heat radiating in or out of this object at each different point on the surface, or rather the total amount of heat because we're integrating it along the entire surface. So this would be an application of a surface integral. So we can just illustrate the calculation procedure through a simple example. So we'll just look at a scalar function first. So it would be a surface integral of a scalar function. We can have some kind of scalar function d, which is equal to x times y times z, and this is being integrated along a surface, and that surface is a cylinder. X squared plus y squared is equal to 4, and this cylinder is bound between z is equal to 0 and z is equal to 3. And we'll say it happens in the first octant. Okay, so what are we determining? We're determining the surface integral of this scalar function multiplied by this vector area. So the first thing that we need to determine is actually the normal vector, because this is what the surface, this vector area depends on. So to determine the normal vector, we have to create some kind of implicit function, and then find the gradient vector of that scale of that implicit function. So the implicit function, which is phi, would become x squared plus y squared minus 4. And then we know that the gradient vector, or grad, is just the derivative of that function with respect to x in the in the x direction, and then the derivative with respect to y in the j direction, and with respect to z in the k direction. So if we do that, then this gradient vector just simply becomes 2x times I plus 2y times j. And yeah, that's it. There is no k component. So the magnitude of this gradient vector is just simply the square root of each of the components squared of the gradient vector. So that becomes 4x squared plus 4y squared. So we can see that we can pull out the square root of 4 as a common factor. And then we're left with the square root of x squared plus y squared. And x squared plus y squared is equal to 4, which is what we had seen from the question. So that becomes the square root of 4 times the square root of 4, which is just 2 times 2, which is 4. So the unit normal vector is simply just this gradient vector divided by the magnitude of the gradient vector. So essentially we're dividing 2 by 4, that gives us a half, and we're left with x plus y. X plus y in the directions I and j. So now that we have the unit normal vector, what we're actually needing to compute is this surface integral. So we can do it by considering our surface. Well, what is our surface? Our surface is a cylinder, and we can just draw it here quickly. That's x, y, and z. Okay, so z is equal to 0 and z is equal to 3. That's the boundary of our integral. And we can take a differential surface area element along the surface of the cylinder, ds. And since we're doing it along the surface and the radius is already defined, the radius of the surface of this cylinder is 2. That's been given in the question, because x squared plus y squared is equal to 2. Is equal to 4, and 2 is the radius. So this is dz, and this is simply just depending on the angle. So the angle will be d theta, and that's r. So that's r d theta, and the radius we know is 2. So ds is just merely length times breadth. So it's dz times r d theta, and r is 2. So ds is equal to 2 times dz times d theta. But when we now multiply this by the unit normal vector, so the unit normal vector multiplied by ds is equal to, so 2 times a half just gives us 1. So we're left with xi plus yj times dz d theta. So now we're in a position to determine this. If we do that, the integral along the surface of d times ds. So this is what ds is equal to. That's the vector area. And you'd recall that d was just x, y, z. So that's also stipulated in the problem. So we just substitute that in. So we're doing a multiple integration with respect to dz and d theta. So z would be integrated from 0 to 3. That's the boundary given to us. And theta is going from 0 to 90 degrees because it's only in the first octant. So theta would go from 0 to pi over 2, and z is going from 0 to 3. And we're determining the integral of x, y, z into xi plus yj times dz d theta. And then expanding this out, we get x squared times y times z times I plus x y squared times z in the j direction, and of course dz d theta. So our variables are in terms of x, y, and z, but we're integrating with respect to z and theta. So we have to convert x and y to be in terms of theta. So how do we do that? Well, we use polar coordinates. So we would remember that x is just r cos theta and y is r sine theta. And radius is 2, which we see from the question. So we just substitute these things in. So we go from 0 to pi over 2, 0 to 3, and then x squared. So we have 2 squared times cos squared theta multiplied by y. And so 2 times 4 is 8. So we have 8 cos squared theta times sine theta in the direction of I. And let's not forget z as well. So z is here, so we have to substitute that in. And then here we have x, so 2 cos theta times y squared. So it's again 2 squared, which is 4. 4 times 2 is 8. We have 8 cos theta sine squared theta times z in the y direction, and then dz d theta. So we're just integrating with respect to z first, and the integral of z is just a half z squared. So we can bring that out. So we have all of this just multiplied by a half z squared, and all of that multiplied by a half z squared, being integrated from 0 to 3. So we have the integral of half z squared integrated from 0 to 3, and the rest of it. Integral from 0 to pi over 2. We can bring out the h as well, so we'll just put the h in front here. So what we're left with is cos squared theta times sine theta in the direction of I, plus cos theta sine squared theta in the direction of j, and just the d theta is left. So 8 divided by 2 is 4, so we have a 4 in front, and 2 z squared, so 3 squared is 9, so 9 times 4 is 36. We have 36 into all of this stuff, so let's just integrate that. So the integral of cos squared theta times sine theta, so that's just cos cubed theta. So if we find that, we integrate cos cubed theta. So the 3 will come to the front, so we have to divide it by 1 over 3. And the derivative of cos is minus sine, so there's a positive here, so we have to account for that positive being there as well, so we have to put a negative in front. And then integrating this, the integral of sine squared cos is just sine cubed. And also we have to bring in a 1 over 3 in the front. This is integrated from 0 to pi over 2. So it's a fairly simple matter just to substitute these things in. The cos of pi over 2 is 0, and let's just do this first. Bring the 1 over 3 in front, so 36 divided by 3 is 12. So cos of pi over 2 is 0, and then sine of pi over 2 is 1, so we have j. And putting in 0 there, we have cos of 0, which is 1, and then minus and minus gives us a plus, so we're left with I. So this is our final answer, finding the surface integral of the product of the scalar function and vector area. We can also take the surface area with respect to a vector field. So we can illustrate that with just a basic example. So in this instance here, what we're doing is taking the surface integral of some kind of vector function f and multiplying that, taking the dot product with the vector area along a certain surface. So let's just say we have some kind of vector function f, which is equal to yi plus 2j plus k. And this is taken with respect over some surface, and that surface is given by the sphere x squared plus y squared plus z squared is equal to 9. So it's a sphere with radius 3 essentially, and it's bounded by x is equal to 0, y is equal to 0, and z is equal to 0. So it's essentially in the first octant that we are considering it. So as was the case in the previous example, we start off by determining the normal vector, and we need the gradient vector to do that, and it follows the same procedure as the last example. So the gradient vector is 2xi plus 2yj plus 2zk. And the magnitude of the gradient vector is given as the square root of 4x squared plus 4y squared plus 4z squared. So that's the square root of 4 multiplied by x squared plus y squared plus z squared, which is equal to 9. So that's just 2 times 3, which is equal to 6. So dividing these two to get the unit normal vector, it's just 2 divided by 6, which is 1 over 3. And what's left, it's just xi plus yj plus zk. So now we need to take this over the surface that we're integrating. And that surface is a sphere. So it's easiest to use spherical coordinates. So let's try and just see how we're going to do that. So in the first octant, the sphere is going to look something like that. Its radius is 3, so it'll be 3 on all of the axes. And now we can consider some kind of differential surface area element. So we'll just take a surface area element like that, and we will try and convert that to spherical coordinates. We'll take our point, we'll take that as the point, and we know that to work in spherical coordinates, we have 3 variables. They are rho, which is actually the radius of the sphere, so that's rho. And then we have phi, that's the angle between the z-axis and rho, so that's actually phi right here. And that's also the angle if we were to make a projection in terms of the xy plane. So that angle is phi as well. And also theta. So theta is the angle between the x plane and the line that we're considering, the projection. And that's 90 degrees. So we can convert everything to be in terms of these different variables. So there's also some kind of variable r. So r is just the distance between the point of origin and to the projection on the xy plane, that the point projected in the xy plane. So let's try and understand what the surface area element is going to be. So this is r, okay, what I've just drawn there. It's the same thing. It just projected on the point at the top here. And then this angle is theta, so it's d theta actually. And we know now that that length is going to be r d theta. And of course, this length of that line is rho, and the angle is phi. So this length of the surface area element is actually phi, or rho d phi. So the surface area element is actually r d theta multiplied by rho d phi. So we now need to convert r to be in terms of rho. It's a fairly simple thing to do. We just write that sine of phi is equal to r over rho. We can see that's a 90-degree angle there. So sine of phi is opposite over hypotenuse. The opposite is r, and rho is the hypotenuse. So what this implies is that r is equal to rho sine phi, and we can just substitute that into ds. So it means that ds is equal to rho sine phi okay, so there's rho and then rho, So rho times rho is rho squared, so don't forget to write the rho squared there. It's rho squared sine phi d phi d theta. So we have our differential surface area element and we have our normal vector. So all we do is just we multiply this too. But as was the case in the previous example, we have to convert between x, y, and z to be in terms of rho, phi, and theta. So how do we go about doing that? Well, you can revise our video on spherical coordinates. And if you do that, you will see that x is just equal to rho sine of phi sine theta, and y is, sorry, I just made an error here. So this is actually supposed to be cos of theta. So y is actually rho sine phi sine theta. And then lastly, z is equal to rho cos phi. So that's what we've got to do. We've got to substitute these things here, what x, y, and z is, into x, y, and z. Replace them to be in terms of rho, phi, and theta. So now that we have all the information to determine the surface integral, we can actually proceed to perform the integration, or to actually set up the integral. We would remember that we have to integrate over the surface of some vector function f multiplied by the vector area ds. So this is actually equal to the integral over that surface of this vector area multiplied by ds, rather dot product, and integrating with respect to ds, and also multiplied by the normal vector. We can do this quite easily. So f was given earlier in the problem, so that was equal to yi plus 2j plus k. And the normal vector was also determined earlier, and we saw that it was actually 1 over 3 into xi plus yj plus zk. The differential area element ds, that was also determined. Just remember that rho squared, so rho was 3 because it's the surface area, or rather it's the radius of the sphere. We can substitute that in. So that's just 9 times sine phi times d phi times d theta. So proceeding in this manner, I'm substituting all of these things in. Remember that when we're taking the dot product, I times I gives us 1 and I times j gives us 0. So all the perpendicular products give us 0. So what this means is that this is equal to, let's write it here at the bottom, integral across the surface of f dot ds is equal to, firstly, I times I gives us 1. We already spoke about that. So we have 1 over 3 multiplied by 9. That is just 3. So we have 3 into xy plus 2y plus z, and then multiplied by ds, which is sine of phi d phi d theta. So this has to be integrated across the surface. And if we look at our sphere, we need to integrate with respect to d phi and d theta. So since it's in the first octant, we can see that theta goes from 0 to pi over 2, 90 degrees. And also phi, this angle goes from 0 to pi over 2. So it's also 90 degrees. We can just put that in. And also we have to convert between x, y, and z, and rho, theta, and phi. And we can do that by just performing those substitutions as explained earlier. So when we do all of that, we make those substitutions, what we get is that, firstly, we won't put in the integral bounds just yet. So we'll just say that f dot ds is equal to 3 into 3 sine phi cos theta So I just substitute in what x and y is. Plus 6 sine phi sine theta. Okay, I just missed out a square here. And lastly, z is just 3 cos phi, and also d phi d theta. So integrating this, it's fairly straightforward. All we have to do is just integrate this, and then integrate from 0 to pi over 2. And also a 0 to pi over 2. So the only maybe difficult thing to do in this integral is to integrate sine squared phi. And that's not difficult as well. We just have to remember that the integral of sine squared phi is just half phi minus 1 over 4 sine of 2 phi. So this is just a standard integral, and you're integrating this from 0 to pi over 2. So once you do that, the rest is quite straightforward. So I won't do this here. I think just attempt it on your own and try to find the answer. It's fairly standard. So thank you very much for watching. And in the coming videos, we're just going to discuss conservative vector fields and divergence theorem, Stokes' theorem, and Green's theorem.